My graduate advisor at UC Riverside, and recently he moved to Ohio State. Before the introduction, I would like to say I'm always thankful to Roland because he introduced me to the research full of excitement, and that led me to where I am now. And okay, back to the introduction. He did his graduate study at Berkeley, where he worked with Zichang Chiu on magnetic couplings and quantum well states in magnetic multilayers. He got his PhD in 1999. Then he moved to UC Santa Barbara for a postdoc. And that's the time spintronics became a really hot field. And in there, he worked with David Ashlong for 3 years. His most famous work at that time was imprinting of nuclear spins in semiconductors, studied with ultrafast optics. Then in 2002, he joined UC Riverside as an assistant professor, and that's the research group I worked as a graduate student. Then, of course, a few years later, he became a professor. I would like to mention that in Riverside, he built really a fantastic lab there. To give one example, they had a materials growth system using molecular beam epitaxy, and the system was capable of doing in situ transport measurement, in situ optics measurement, down to helium temperature and also in magnetic field. And the lab he's building now at Ohio State, I'm sure it's even better. So, well, what's more important is the research came out of the group. So they did a series of beautiful work on spin transport in graphene, and more recently also in other 2D materials. And that's the talk we're going to hear today.
Oh, wow. Thanks a lot for the great introduction. This is my first time to this university, and I'm really happy that Sarah has landed in such a wonderful place. I talked to a lot of faculty here. I think it's really, really nice. Yeah, and so she was one of my first students, not my first student. And I had a generation of students, well, who are like my superstar students. So all these ones with numbers. And what a fantastic generation. And Yan was was the first one of the bunch, actually. So she joined my group. I think I was there for a couple of years, and I was like tearing out my hair. I was like, oh no, these students I have, this is no good. And then I had Sarah and Kyle. They came in together, and they completely changed how the research was. I mean, they were very serious and worked hard and got everything running. And to get a lab running from scratch, effectively, that's where it was at that stage. It's a lot of work, a lot of dedication and determination, and she definitely has this. And so she worked very closely, and all these are sort of the junior students, and they really followed her lead, and the entire team turned out to be really great. And they all just graduated, and I feel sad a little bit. I was like, there's going to be a big drop-off in productivity after these guys, and that's sort of happened. But yeah, and they've all done very well. Of course, Sarah is here, and these younger students are in their postdocs with Stuart Parkin's group and Barry Yonker, Harold Wong. So these guys do a lot of really nice work in spintronics. He does very nice work in oxide interfaces, and he's the most rich, the one at Headway Technologies. It's a startup. He got lured away from a bigger company. And also, Weiwa, he's a faculty at Academia Sinica in Taiwan, which is a very good place. Yeah, and so I'm just so excited to have been able to work with such wonderful students at Riverside. Okay, and then, so I guess for my other acknowledgements, some theory collaborator, Yaroslav Fabian, is very important, and also Jeannie Lau is a colleague of mine at UC Riverside. She's fantastic as well. And so what I want to tell you about today is I had to select some portion of the research that I wanted to present. So I want to tell you about spin transport in graphene. And I wrote and beyond, and this was sort of a last-minute type of thing. So beyond, nowadays there's lots of other 2D materials that are being studied, MOS2, silicene, germanine, and I'll tell you about that. So, you know, some people just call that, yeah, that's graphene, and they use that word for everything. So Graphene Week, they say yes. Well, when we say Graphene Week, we mean everything 2D materials. And other people, they write beyond graphene, but so that's what I mean. And I'll tell you about at least our preliminary work in this area. I'm really excited about some of the materials work is just 2 weeks old, and I just put it in. I just have to tell you about it. Okay, so here's my outline. I'll give you an introduction about spintronics a little bit, not so much, but more about graphene and graphene spintronics and how the field has developed. Then I'll tell you mainly about 3 scientific results. One is spin transport and spin relaxation in graphene. I'll also tell you about, well, Sarah was telling you about this very special system. So we actually did some in situ spin transport measurements on hydrogen-doped graphene, where we see the formation of magnetic moments and exchange fields. So this, we really capped off a lot of nice work that we had done. And I felt this was a very special result that really required the machine that we had spent many, many months building. And then finally, I'll tell you about some 2D materials beyond graphene, and specifically germanane. So this is like graphene, but you replace the carbon with germanium. And we're able to grow this by MBE. And I'll just show you the materials work that we've done. Okay. So I think, you know, many people know about graphene, but those very few people who don't. It's basically graphite is the layers of carbon, and each individual stack, if you pull it out, that's called graphene. And the band structure, the electronic properties are quite different. I don't like this side so much. I'm not sure what I'm going to do. Oh, this works. Okay, I got more room here. And so in graphite, it's a semi-metal. Here's the upper band and the lower band, and they cross. But when you have a single layer, you get a very different band structure. It's a linear band structure. It's relativistic-like. And because it's very thin, you could apply electrostatic gates, and you could tune the Fermi levels, so you could have electrons or holes. And nowadays, this material can be made by chemical vapor deposition very well. But it's still very useful to just use the old method of Scotch tape, and you could exfoliate small pieces of graphene. And why it's interesting for spintronics is that because it's made out of carbon, then you have a low intrinsic spin orbit coupling, and also because most of carbon doesn't have nuclear spins, and also because these are pi orbitals, so you don't have contact hyperfine interaction, then your hyperfine coupling will be very weak. So the interaction with nuclear spins is very small. And typically that's not a good thing for having spins try to live a long time. And also the material has high mobility. And so you put these together, there's a possibility for a very long spin lifetime and also long spin diffusion lengths. Okay, so this is sort of the original motivation. Let's try this material out. And I just want to give you some sense about how the field developed. I mean, one thing I would say is that if you compare at room temperature the spin diffusion length, so this is how far electron spins will diffuse before they depolarize. If you look at metals, I think it's a little better than this now, but it's on the sub-micron level. Silicon at room temperature is up 0.6 microns. I think that's improved a little bit. And graphene, I would say a reliable number is between 3 and 10 microns, although people have reported higher. People have reported as high as 100 microns, but I don't know if I trust that. But anyways, if you compare to the other materials, the spin diffusion lengths are really quite good. In terms of the experimental groups, it's actually quite international. There's the Van Wees group, which I would say is really the biggest pioneer in the group, and our group in the U.S., Shiorishi's group in Japan, a nice graphene group in Singapore and Germany. Albert Furt works on this. Sergio Valenzuela has some nice results. So it's a very international type of effort. And I want to highlight there's been quite a lot of advances since 2007 when this field really took off. And so this work by Van Wees showed that you can have room temperature spin transport and a few micron spin diffusion length. And he also saw spin precession, which really proved that it was indeed a spin signal as opposed to some artifact. And I think the next really important advance was the development of tunnel barriers for spin injection. So this, and I'll tell you about this in this talk, this really improved the spin injection efficiencies, and more importantly, it improved the spin lifetimes. There was a big mystery, which I'll tell you about in terms of spin lifetimes. They're way too short. And we're trying to understand, well, what causes them to be too short? And so I would say most of the work in the field these days is focusing on trying to make better and better tunnel barriers. And this is really the first work that went in this direction. And there's a lot of studies of what's causing the spin lifetime to be shorter than expected. And now it's been expanded to CVD-grown material. And recently there's been some work on spin pumping and also on spin Hall effect that's induced by atoms. So these are the very latest work. So it's a really exciting field, a lot of work going on, and a lot of advances taking place. Because there's also some interest technologically. I mean, I would say it's far off. But because you have these long spin diffusion lengths at room temperature, there's a chance you could imagine trying to integrate storage, like memory and logic, for high-speed and low-power electronics. So there were various device ideas that were developed, not for graphene initially, but for semiconductors. And they said, yeah, if you had a semiconductor spin channel and you put ferromagnetic metals on and you had lateral spin transport, then you can have some type of integrated storage and logic. And here's another, this is by Liu Sham's group. There's another proposal by Dada's group, and they had envisioned this in metals. And it turns out if you take these ideas, but you say, I want to do it with graphene and use the numbers that graphene has, then it works a lot better in graphene than you can do it in metals or semiconductors. So there's, you know, so actually part of some effort to try to develop some prototype devices in this direction. I won't tell you too much about applications. This is like it. So I'll focus more on the physics. The other thing that's really cool about graphene, not only is it two-dimensional in terms of two-dimensional physics, but it's actually a two-dimensional crystal where you have a surface that's really exposed. Right? So because of that, you can modify the properties. You could put atoms on top of it, and that could potentially modify the properties. And I'll tell you about work there. You can also grow, it turns out you can grow complex oxides on graphene by MBE, molecular beam epitaxy. This was a surprising result for us. And I was going to tell you about it, but I took this out, deleted this part, and added the new stuff on the 2D materials that are hot off the presses. And the type of things that you could do is you could change certain properties. You could make it magnetic, possibly, and introduce exchange fields, which I'll describe a little more. You could induce spin-orbit coupling. This was done by the group in Singapore to see the spin Hall effect. And if you could induce these type of interactions, then you can maybe get 2D topological insulators, spin Hall effect, anomalous Hall effect, quantum anomalous Hall effect, and gate-tunable magnetism. So there's a lot of interesting physics that could happen if you could just create these type of interactions. So we've been trying to develop these type of hybrid systems to try to realize some interesting physics. Okay, so since I mentioned exchange fields, I'll just explain what I mean by that. And it's that whenever you have two spins and they can overlap quantum mechanically, you can generate an exchange coupling, and it's basically some constant, which is various integrals of wave functions if you look at it. But you basically have a dot product of the two spins. So if they're parallel or anti-parallel, you'll have a different energy. So the exchange coupling is something that is needed to make ferromagnets have their magnetic moments line up. Okay? But it looks like this. So imagine if you had a conduction electron here, say inside the graphene, and you had a magnetic moment or a ferromagnet magnetization. You could just rewrite this. I just moved around some terms. And you can make it look like a magnetic, the spin of the electron times an effective magnetic field, which is really the magnetization. And so this field can be, you know, hundreds of Tesla, possibly. All right? And it's not a real magnetic field, but it acts like one. But its origin is completely quantum mechanics. Okay? So it would be nice to be able to have that. Why is because then you have a chance to manipulate the conduction electron spin polarization. For example, if you had electron spin inside graphene, and you had a magnetic insulator and a gate, what you could do is you could charge up the gate, and you could either repel the electron in here, and in this case you're far away, so the exchange field will be 0. If you attract the electron, you'll get some wave function overlaps, and then you can get some exchange field. And just by changing this voltage, you could change this internal or local magnetic field. It's an effective field. Or you could have the magnetization inside the graphene, and then this electron spin can interact with all these magnetic moments, and you could have spin precession. So if you have this exchange field, you can have spin precession, and you can manipulate those spins. Okay? And it turns out there's quite a number of theory papers, and I love theory papers. They make everything seem so easy. Right? Especially this one. Look at this. That is so easy. They say, so at first they said, yes, what if you had spin transport and you had proximity-induced ferromagnetic graphene? So you can make graphene act like a ferromagnet. All you got to do is put next to it a magnetic insulator, like here. Or you could get this quantum anomalous Hall effect in single-layer and bilayer graphene. Just do it. Or if you had a bilayer, you could actually use electric field to control the spin rotation. You could rotate spins just by applying different gate voltages. So that's a little bit like what I just showed you last slide. So if you could do this, this would be really great. And so there's been sort of a quest among some of us to try to realize these exchange fields basically in every semiconductor, but especially in graphene.
So why is the exchange so phenomenally large?
Well, why is it so large?
Because you said like hundreds of Tesla.
It could be.
I would say, yeah, right. But
it originates from, oh, sorry.
An impurity is localized, and then you have these delocalized conduction elements.
Yeah, yeah. So it could be large because it originates from the Coulomb interaction, so it's like a Coulomb exchange. So, I mean, the energy scales for magnetism are really small, like micro-EV-like, whereas in exchange couplings can be MeV or even EV level. Like inside ferromagnets, it's at the electron volt level. So it's because it's really originating from a charge and a quantum mechanical effect. It could just be a lot larger, right?
But, I mean, you can have a large field for a ferromagnet.
Yes.
Same thing, basically, isn't it?
Not exactly the same thing.
The interaction of a magnetic impurity with delocalized states.
Yeah.
So, and because of the delocalized states, I would say exchange integral is small. I mean, I may not. That's my question. What do I not get here?
I think you are not incorrect. So, no, I think you're right, actually. So later on in the talk, I will mention about hydrogen atoms creating magnetic moments, and the exchange field is pretty large, larger than expected. And Jaroslav Fabian developed a theory. He says, how can it be so large? Is because the wave function must be localizing to make it large. So he's proposed this idea of resonant enhancement of exchange coupling. So yeah. So if it was this small thing and it was completely delocalized, it would be bad. It would be small, like you would have in the hyperfine coupling. You want them to be more localized. Yeah. So that could play a role in all that. Yeah. Okay. So I want to tell you about the experiments that we're doing on spin transport, and I'm not assuming people are familiar with this. So it's a little bit pedagogical, but but it is a little bit different than magnetoresistance measurements that are typically done in spintronics. So the device geometry is we have this red strip, which is graphene, and we put on magnetic electrodes. They're going to serve as spin injectors and spin detectors, and sometimes we have tunnel barriers, sometimes we don't.
That looks almost as easy as theory.
I know, done by PowerPoint. And then there's two outer electrodes, which are typically non-magnetic, but in our early studies we also used cobalt, so that's a trick. And then there's a insulating layer, and the silicon substrate is conducting, and you apply a gate, a voltage to the substrate, and this acts as an electrostatic gate. And let me just show you a picture of the device. So here's a strip of graphene, and then there's a bunch of metal electrodes. These are all cobalt. So the big trick was, ideally you want to have these to be gold, but if you're Bart van Wees, you're very smart and you just make them all cobalt. So you have huge numbers of sets of 4 to do your experiments on. And the fact that these outside produces some extra junk is not that important, initially anyway. And the other point is that if you apply a voltage to the gate, this is like a capacitor, and what happens is that if you put a positive charge on there, it will attract electrons into the graphene. If you put a negative charge, it'll attract holes. So you can control the carrier density just by applying this backgate voltage. So you're able to tune this material. You can do this with semiconductors, but say in metals, you couldn't do this type of tuning so easily. Okay. Now this is in the field it's called the non-local spin transport measurement. And so what you do is uh-oh, it skipped a slide. Well, what you do is you flow a current through this ferromagnet into the graphene and out the non-magnetic side. And what that does is that's going to inject a spin-polarized electron. Because these ferromagnets, they don't have equal numbers of spin-up and spin-down electrons. They have more of one than the other. So ferromagnet is a spin-polarized material. Okay? And so when you drive the current, you're going to make a spin imbalance. So these red is the conduction electrons inside the graphene. And what happens is that the charge current flows to the left through this loop. But spins have a mind of their own. Some of them get pushed to the left, but other ones just decide to diffuse. They diffuse in all directions, actually. And some of them decide to just diffuse to the right. And when they reach the second ferromagnetic electrode, this is a ferromagnetic spin detector. And what you do is that you measure the voltage between that and a non-magnetic electrode. And the voltage will tell you the spin polarization underneath this electrode. Okay, and this is called a pure spin diffusion current or a pure spin current. And conceptually, the way I like to think is that if you had a bunch of spin-up electrons going to the right and a bunch of spin-down electrons going to the left, you see there's a net flow of spin, of angular momentum, right? But overall, there's no net flow of charge, right? So that's the type of behavior that's happening in this middle region. No charge, no net charge flow, but there's a net flow of spin.
So is there separation between blue to blue is like micron dimension?
Yeah, so we've gone as high as about 5 or 6 microns.
So that's how you measure the spin diffusion length?
No.
Oh, so
Yes and no. Yes and no. So there's a way to extract the spin diffusion length, which I will tell you about. So if you had your, so we've taken this down to half a micron and up to about 5 or 6 microns, and we can get signal. So there's a way to do that, to get the spin diffusion length in a slightly different way, which I'll tell you. But if you want to say, well, I have a very long spin diffusion length and it's like 20 microns, the proper experiment is to put them 20 microns apart and measure it, right? So so I would say that's a direct measurement of how far they can travel. But there are ways to extract that number by having the electrodes much shorter. So early on I said there was 100 micron claimed, but those electrodes were 2 microns apart. So it was extracted based on some theory, essentially. Okay, so I don't fully trust that. But I'll tell you how it's done typically. So the injection works like this. You have more spin ups than spin down in the ferromagnet. And when you apply a bias, then you're going to inject some electrons. And what happens is, since there's more spin ups, you're going to start filling the spin up bands faster than the spin down bands. And what happens is you start getting a chemical potential, which is like a local voltage. It's just going to be higher for spin up than spin down, right? So it's sort of almost synonymous to have a splitting of this spin-dependent chemical potential to correspond to your spin density, okay? And this is why the measurement works. So you get a splitting between up and down. So over here at the injector, you have a spin up chemical potential, a spin down chemical potential. And as you go to the right, what happens is, because you have spin flip scattering, you start depolarizing the spins as you go to the right. And so the overall spin density is going to decay, okay? And the way the detection works is, if you have a spin-up detector, it's going to measure the voltage, the local voltage, this mu up of the spin-up. Whereas if your detector has opposite spin polarization from your injector, then you're going to measure the spin down chemical potential, right? So this is how the spin polarization gets converted into a voltage that we measure. And there's a whole bunch of background signals. So what you typically do is compare the parallel configuration with the anti-parallel configuration. And typically you normalize by the injection current. I mean, if you pump more current in, you'll get more spin density and your signal will be bigger. Okay, so typically you'll normalize this, and this is typically called the non-local magneto resistance, because it's voltage divided by current. And this is a typical data set, and this is for real. So what you do is you'll start with this type of geometry, and you'll have these 2 electrodes, the injector and the detector. You'll start with them, say, parallel. A large negative field makes them parallel. You start increasing the field, and at some point, one of these 2 ferromagnets will flip over. And then you see a big jump. And then finally, at another field, the second one will flip over, and then you'll see another jump. So they go from being parallel pointing down to anti-parallel to parallel pointing up. And then you'll go from positive to negative. You'll see the same thing, but since the ferromagnets are hysteretic, you'll start positive, parallel, and then anti-parallel, and then parallel. And these extra little jumps are because if you want to do one-step lithography, you can make these outside guys ferromagnetic too. But that's a small effect. It's not a big deal. Okay? And the efficiency of the spin injection, the polarization of the injected carriers is about 1%. So that's not too high. Okay.
The magnetic field doesn't affect the diffusion at all.
The magnetic field could, in principle, affect the diffusion, but we haven't seen any effects of that. And even the presence of spin density, that should give you different diffusion coefficients for a spin up and spin down electron. We haven't seen that in our systems, but in gallium arsenide, now people are able to inject with such high polarization and density that these chemical potentials split so far that you start seeing signatures, and it's basically various new asymmetries that come out, like higher order effects, where the presence of spin is going to affect the flow of the following spin. So we don't see that because I don't think we're driving it hard enough to see it. But that type of effect you're mentioning, or related to what you're mentioning, has been seen in gallium arsenide recently. Yeah.
I like to think of spin diffusion as mutual spin flips that conserve energy, and the thing that limits the rate of spin diffusion is things that can cause the energy levels, splittings of neighbors to be somewhat different. For instance,
Correct.
impurities can do that.
Correct.
So I was wondering what is limiting your spin diffusion rate in this case.
Yeah, I don't think it's that. I mean, so if you're talking about nuclear spins, for sure, right? It's going to be spin flip for sure, because the nuclear spins can't move. Well, that could happen. I don't know. I mean, that.
You still conserve energy.
Yeah, I mean, that's definitely possible. That could be the case. I mean, I think because these are associated with electrons that can move. So the way I typically look at it is, they sort of bounce around, and so I think the driving force on this is not the spin flip-flop diffusion, but more the electron.
So it's actually motion.
The motion of the electrons is really what's driving this.
Spin diffusion. It's diffusion of spins. That's a different thing. Spin
yes.
diffusion doesn't necessarily involve
That's right.
particle transport.
That's right. So, yeah, it's diffusion of spin polarized electrons, I guess. Something like that.
This is related to
they could
completely different definitions of that term.
Yep.
In NMR.
Exactly.
In the spintronic.
Exactly. So
it's the same term.
It's the same term but different meaning. Yeah.
Different meanings.
Yeah.
I would think as long as you see a Hanle effect, that kind of process can be excluded. You wouldn't see a Hanle effect. You wouldn't have a propagation while they a spin propagation while they propagate spatially.
Is that right?
Yeah.
I'll have to think about that.
No, there are Hanle effects. I mean,
Yeah.
That was observed in 2007 already.
Yeah. So well, I have to think about. For sure, there's Hanle effect. I mean, okay, I'll show it to you here.
Right.
But I'm just thinking if it would rule out that type of spin diffusion.
This
Okay.
kind of spin diffusion is more or less a relaxation process, right? A kind of
It could be.
Yeah.
It could be, but it can also actually diffuse too. So, I mean,
It's a diffusion of energy rather than
Yeah.
particles.
So there are these Hanle measurements that were just mentioned. So the idea is, if you're wondering if this is a real, like, say, electrons diffusion of spins, electron spin diffusion, or if it's some other magnetic field-driven artifact, this is the key measurement. So what you do is you apply an out-of-plane magnetic field, and that will cause the spins to precess. And then what happens is that essentially this large signal that you get will start to depolarize. And you can even see some oscillations because these can oscillate. But you get this kind of peak. And for the anti-parallel case, you have a negative voltage, and you'll see a flip over of that first peak. Okay? And once you start seeing these Hanle effects, then you realize, yes, the signal that we're seeing is really from electron spin transport. Okay? As opposed to some kind of Hall effect induced by the magnetic fields generated by the electrodes or anything like that. And so this is one of our early ones. And what you can do, so the way that you deal with this theoretically, and this is not the most fancy way, there's more fancy ways, but the idea is you have a term that comes from the electron diffusion, so D is the diffusion constant. you have a term which is from the lawnmower precession, the precession of those electrons. And then you have a term that you have from the decay, the depolarization, the relaxation of the spins. And you put all that together because it's a steady state, and you can get these curves. And so what people typically do is they will fit these curves, and based on the fits, you can extract out the diffusion coefficient, and you can extract out the spin lifetime. So the typical way for people to get a spin diffusion length is to multiply these two numbers and take the square root. And they say, okay, that's the spin diffusion length. And so typically it's like 2 to 3 microns in these materials. And so in the first works that came out by Van Wees, all the lifetimes were like 100 picoseconds. I think 150 was the highest. And we see, okay, it's like 80, 84, okay? And so one question is, why is this so short? Because it should be long. Theoretically, it should be like maybe a microsecond. And this is much, like orders of magnitude shorter. And so this is still one of the mysteries of the field. But so what's causing all these problems? Okay, so when we were early in the field, we noticed that the injection efficiencies were pretty low, and the lifetimes were very low. So this was some issue. And so the question is, what's going on? And even now, the question is still, what's going on? And so one of the big problems that comes about is this thing called the conductance mismatch. And it sort of works like this in a cartoon picture. So what happens is I have a metal contact, and I have graphene. Now graphene is a pretty good conductor, but it's not quite metallic conductivities. Okay? And what happens is, let's say we try to inject some spin. So we're going to inject some spin up. But then once the spins are inside, they could diffuse in all directions. They could diffuse along the charge current. They could diffuse in the other direction. But they could also diffuse back into the cobalt electrode. And sort of the rule of thumb is they'll naturally diffuse to low resistance regions. Right? So since the cobalt is the lowest resistance region, a lot of it will backflow into your injector. And this is a known problem in semiconductor spintronics. So you have to somehow get around this problem. And it's known even theoretically and experimentally how to do it. But what you do is you put a tunnel barrier in, and then so you inject with a bias to get the stuff in. But then, it's going to have a hard time backflowing because this tunnel barrier, like MgO tunnel barrier, will prevent a lot of this backflow, and it will allow the spins to stay inside the graphene. So this is the conductivity mismatch problem, and this is a solution to get around it. Okay. So we tried to do that at first, and we had some success. So we put in a MgO tunnel barrier, or we put in a barrier, we just grew it, and we went from 1% to 8%. And so we were happy. I mean, our signals are getting bigger, and everything's nice. But we noticed that it wasn't actually a tunnel barrier. We looked at the temperature dependence, we looked at the IV curves. It looked like an ohmic contact, except higher resistance values. And when we looked under AFM, we grew on graphite, and it was pretty rough. So we said, that's not good. So we developed a trick. Instead of just growing the MgO on top of graphite directly, we started with a titanium seed layer. So in fact, it's only a half atomic layer that we put down first. And then when you grow the MgO on top, it's a lot flatter. This is just the AFM scans. And yeah, so basically what the titanium is doing is it's inhibiting the diffusion of atoms on the surface. It's like a sticking layer. And then we also oxidize it so that it's an insulator. And then we grow on top, and it's a very nice layer. And it took us about a year or so to get this to work, but it does. So,
choose titanium?
how do we choose it? It was in our chamber.
That's a good idea.
I don't know why it was in our chamber, actually. I don't know. We had tried to do it without an adhesion layer for a long time, and nothing was getting better. And
so it's a standard adhesion layer.
Yeah.
For many processes.
Yeah. In clean room processing, it's standard, but typically it's pretty thick. So if you try to put gold on a device, it'll like peel off because it doesn't react. So we knew that it was a very favorite one, and we didn't want to use things like chromium, which also get used because that's magnetic and all that. So we said we wanted something that's non-magnetic and and sticks. And so we had this type of contact, which is a direct contact, and we had this kind of contact, which was a tunneling contact. Well, we weren't even sure it was tunneling initially until we did some electrical measurements. And what we find is that not only does the size of the signal in terms of this, ohms change, so it went from milliohms to, so it went up by 2,000, but actually you can extract out the spin polarization. It went from 1% to about 30%. And this is, the cobalt itself is somewhere between 30 and 40. So this is about as high as you can get without fancier tricks or fancier materials. So this was a very nice advance, and so it was sort of the numbers that came out of this work that were plugged into all these magnetologic devices and said, hey, this should be the best material. Although we don't get this all the time. We can routinely get 50 ohms or so, but 130 was our biggest we've gotten. Okay, so this was expected, and that's what we saw. But we also learned something that was very surprising, at least to us at the time. Maybe we weren't smart enough to figure this out before the experiment. But here you have a transparent contact. You can have an MgO with pinholes, and then we have this MgO with a titanium adhesion layer. And you start fitting these Hanle curves. And what you notice is it gets narrower and narrower. And typically the more narrow it is, the longer spin lifetime you get. And what we realized was, in fact, the worst thing in the device was the contact. So if you have a contact that's really interacting with the graphene, the tendency is for it to really start killing the spins one way or another. But then if you made a good tunnel barrier to isolate the ferromagnet, then you can have a much larger spin lifetime. So this was a big advance because there was a big mystery. Why is it so short? And so at least we solved the first step, which is the contacts. They better be good. And still, I would say right now, they're still up to about a few nanoseconds. They're still far below theoretical limits. They've improved since this work that I showed you. But it's still unclear what the problems are. I mean, the mobility, so what are the possible things? I mean, one thing is that our graphene has relatively low mobility, and graphene has gone up to high mobilities, and we have not implemented the high mobility graphene yet. So there's a lot of disorder in the system, and we're wondering if we could get rid of that disorder, will that really help the spin lifetimes? And I just want to mention that in terms of tunnel barriers, this is probably the biggest, in terms of number of publications, this is the area where most people have entered the field, trying different oxides, trying different 2D sheets, like hexagonal boron nitride. This is like graphene, but an insulating version of graphene, so this has been implemented. Some people have used some organics and also amorphous carbon. And so there's been lots of different types of tunnel barriers, and they have different properties. And so this is where the field of the spin transport in graphene is right now. Okay, so I want to tell you, I'm looking at the clock, but I want to tell you about something that I found very exciting, is about graphene if you start doping it with atoms, and especially hydrogen. And what I'll tell you is that there's this idea that if you took hydrogen or fluorine or something that will covalently bond to here, that it will create a magnetic moment, not on the hydrogen, but actually inside the graphene. Or if you had a vacancy, it'll do the same type of thing. You're just removing a pi orbital in both cases, and that will create a magnetic moment. And I think theorists all agree that this is correct. Okay? And there's lots of different theories about this, and they even predict ferromagnetic ordering and gate-tunable coupling and gate-tunable Kondo and so forth. But the experiments are really tricky, because if you put a piece of graphite into your squid, your MPMS, you may see a signal, but you don't know what that signal is from. I mean, it could be impurities on your sample holder, or it's known that there's iron impurities sometimes inside your graphite that you buy from the company. And so there's been a lot of studies, but it's been fairly controversial. You could use magnetometer measurements. You could try charge transport measurements. There's been some works with scanning probes and so forth, but experimentally there hasn't been a consensus. And so we really wanted to understand if there indeed are magnetic moments and if you could have magnetic ordering inside graphene. So this is the same kind of experiment I showed you before, but the big difference is I want to put in a magnetic moment, say with hydrogen, and if you do that, these electron spins that are moving across here, they could interact with the fixed magnetic moment, and the type of interaction you would have is through the exchange interaction that I discussed earlier. And what should happen is that this guy should start depolarizing those electron spins, and then the polarization at the detector should go down. So that's the idea. And what I like about this, it's a localized measurement, so you know what you're measuring is coming from that piece of graphene. and not like somewhere else on your sample, like a sample holder or something. And also the magnetic moment is really a spin, and so we're really directly coupling, well, it's a very simple type of coupling between our electron spin and the localized moment spin, which, well, it's also an electron, but, okay. So to do this was a fancy system. It's our most special system. Actually, we developed this to try to do organic spintronics, okay. But it's basically an ultra-high vacuum system. Inside of it is an electromagnet, and inside here are some electrical probes that could contact the sample. And there's also, you know, evaporators to evaporate hydrogen or cobalt or gold. And originally there was organic stuff there. And so the idea here is we'll make a spin valve, so we'll measure the spin transport, and we'll plop on hydrogen from an atomic hydrogen source. And then we just compare before and after, and we don't take the sample out. In fact, we cool it down to like 10 Kelvin or so, and we put this stuff down, and we measure it right away. So it's probably as the best that we can do, or the best we can imagine doing, all in situ. So first what we do is we look at the resistivity as a function of gate voltage, and this is your Dirac point. This is for the clean graphene. And when you put on hydrogen, this is for 2 seconds worth, this is for 8 seconds worth. I don't know what the coverage is, but based on the change in resistance, we estimate that it's a fraction of a percent. And what you can see is that the resistance goes much higher. What's happening is this localization of electrons that was mentioned earlier, right? And so there's some resonant scattering that's happening from the hydrogen-induced defect, okay? And then we look at the spin signal, and this is basically the signal that I want to understand or explain. So this is a spin valve signal. It looks the typical spin valve signal. But when you start putting hydrogen on, you start noticing there's a dip as a function of magnetic field. And if you put more hydrogen on, the dip is relatively larger. Okay? And so what's happening, the way that I interpret this is at low fields, the magnetic moment from the hydrogen is interacting with these spin polarized electrons and depolarizing them. But then when you apply an external field, you start decoupling in some way the electron spin with the magnetic moment, and so you start recovering the higher spin polarization at the detector. Okay, so we want to do basic, actually most of the experiment was control experiments. I'll just show you a couple of them. So first of all, is it a charge or a spin effect? Because if you look at sort of the theory of what the signal should look like, there's not just the spin diffusion lengths in there, but there's also conductivity. So if the conductivity is changing, then you're going to generate a dip, and has nothing to do with spins, right? So we do, well, a couple of measurements. Well, here. So we looked at the magnetic field dependence, and the conductivity doesn't change, or the resistance doesn't change. And I'll show you a more detailed scan on the next slide. The other thing is it a feature of the background? So I didn't mention, but there's always some background, like a constant background that we subtract off. So is it possible that it's from some weird thing in the background? And the way that you deal with that is you do what's called a minor loop. So you come in here, you go through the dip, and then from the parallel state, you go to anti-parallel state. And instead of completing the hysteresis loop, you just flip it around. And if the dip becomes a peak, then you know it's from spin. If the dip stays a dip, you know it's from background. So it's showing that, yeah, it's really from spin. So we know it's a spin-dependent effect. So we're very happy about that. Oh, this is just to show that the magnetic field dependence of resistance is like, it changes less than 0.17%, and that's just the noise level of our measurement. Right? So the dip can get pretty big, but the charge, the resistance doesn't change at all compared to that. So this rules out, you know, localization effects purely from orbital effects. This rules that type of stuff out. Okay, and I am going to speed up a little bit. So there's this idea of decoupling, which at low fields you'll have this scattering. At high fields, these will decouple. And the way to understand this, actually, Jaroslav Fabian had a model, and I just want to point it out. So the idea is first you have an exchange coupling and an ensemble average of your magnetic moments. And the idea is like you can have this electron spin and it could hop from one defect to the other. And so what happens here is that you take this and you just do some algebra to it, and it basically the exchange interaction looks like an exchange field that fluctuates. and it fluctuates because you're hopping from one to the next. And it turns out whenever you have a fluctuating magnetic field, Yaroslav had worked out the theory for this, and basically the fluctuating fields can generate spin depolarization. And here's the equations. I'm just showing you that they're there. I won't go into it too much. But the point is, I take this type of model of a fluctuating exchange field, and you're able to fit very well, except for maybe at the very tip, but you're able to fit very well the shape of the dip. And for basically every single dip curve we get, we can have a very good agreement in terms of the shape between the theory and the experiment. So it quantitatively accounts well for the line shape of the dip. And the other thing is that it indicates that these magnetic moments are paramagnetic. So we haven't seen any ferromagnetic ordering yet. Even today, we haven't seen it yet, right? But this is showing you something that's kind of neat. I want to tell you that all these measurements were done at a particular carrier density, and it turns out that if you change the carrier density, the relative size of the dip can also change, right? And this is for 8 seconds of hydrogen exposure. This is for 2 seconds, and both of them show a peak. So this exchange coupling effect seems to get strongest at charge neutrality, at the Dirac point. Okay, I'll come back to this in a few slides. The other thing that's neat is that if you have these magnetic moments, you can generate an exchange field, and this is something that we've been wanting to see. And the idea is that not only do you have the external field, but you have the coupling of the electron spin with a magnetic moment, and it will create something that looks like a large field. Okay? And so you'll have the regular field and the exchange field, and you add them all together, and people sort of like to talk about this in terms of an enhanced G factor, so it'll precess faster. Now, we create lots of problems for the field. So first we told everybody that you have to have good tunnel barriers, otherwise your results are junk. This is recorded, huh? Oh well. So that caused big problems, because if you don't have tunnel barriers, then you can't be in the field. Then there was a second problem. This is a big problem, but we've sort of, over the course of a few papers between our group and Van Weese's group, we sort of have agreed a good way to deal with this issue. So before I told you, when you have a longer spin lifetime, you get narrower Hanle curve, right? So we've measured the Hanle, and we said, wow, it's so narrow. The spin lifetime has shot through the roof. We were like so happy. But wait a minute. It turns out that that's one way to make a narrower Hanle. Another way is if you had a faster precession, you'd also get a narrower Hanle. So, well, how do you know which one is which, right? And so there have been papers that have reported, we got really long spin lifetimes, but in fact it's probably not that, it's probably this effect going on, right? So this is a real problem within the field. How do you interpret your data? Okay, so there's a flow chart that is sort of a summary of their work and our work. So here's the deal. The deal is you take the data and you do the standard fitting. You assume that the G factor is 2, no exchange field, and then that'll give you the spin lifetime and the diffusion constant based on the spin measurement. At the same time, you could just get the diffusion constant from Einstein's relation. You take the conductivity, density of states, and so forth, and you calculate this. So these are two completely independent ways to get the diffusion constant. And you say, how do they compare? So if they're similar, so it depends what you consider similar. If they're similar, you say, yeah, let's trust the standard method, and the width is going to be telling you spin lifetimes and so forth. But if you compare this and they're different, so in our case, they were different by about a factor of 8, which is just not physical. And in their work, they're off by a factor of maybe, I don't know, 20 or more, I forget. And so if they're different, then the standard Hanle is not reliable. And so what you have to do is to do an alternate fitting. So what you do is, instead of making the d sub s a fitting parameter, you just take this value and you shove it into this formula, okay, because that's independently made. And then you do a fit in a way to obtain the G star and the spin lifetime. All right, so that's the alternative way. And this actually was developed by Van Wees himself. And we said, wow, that is very elegant. Because in our original work, it was a very complicated method. But this is very simple and nice.
Excuse me?
Yes?
If it's so narrow, you might get some artifact because of the Earth's magnetic field.
If Earth's magnetic field? 0.5 Gauss?
How narrow is narrow in your measurement?
I don't know. I don't know off the top of my head. It's I don't know. I have the data, but it's so narrow. You can't. No. It's so narrow. It's right here. I know. It's right here, and I don't think it's. I don't think it's. No. I'm not sure. I can't. I don't want to be wrong about that.
I also have another question.
Yeah.
So you say maybe the nano due to the faster precession.
Yeah.
Of the spin. And then if I remember several slides before, you say you inject, you induce quantum barrier, right?
Yeah.
And it's getting nano.
Yes.
Is it because something related between?
Yeah.
Because maybe you have some hybridization.
No, that's
between graphite,
yeah.
graphene, and you use some defect
Yeah.
causes.
Yeah, so this effect is not happening in those samples because the DS and DC are pretty similar. Yeah. So I didn't mention it before because it wouldn't make any sense mentioning it back then. But yeah, so all these previous ones, they're fine. And it's only when you have, there's different ways you could generate an enhanced G star. So Van Wees saw it as a localized states can generate enhanced D stars. So he saw that on silicon carbide graphene systems. And for us, we're seeing it from exchange field, essentially. Yeah, so basically after we did this, we're like, well, let's go back and look at all of our data we took for the past, 3 years. And so it was all okay. So, all right, so if you do the standard fitting, we got 4 nanoseconds of lifetime. So we're like, wow. And early on in the study, we really thought we were enhancing our spin lifetime. So we're like, wow, But in the end, we know that it's not right. So, but if you look at the DS and the DC, so the DS is down here and the DC is there, it's off by a factor of about 7 or so. So we just don't trust this fit. And then so we come down here and we use this method, which I would say is not perfect, but it's more reliable than this method. Okay? That's what I would say.
What does that assumption amount to? Assuming D equals DC.
Well, I think it's a good assumption, but there's one thing that's a little, there's some error bars where the error bars come in is that to get the DC, you have to assume a certain amount of broadening for the density of states. You don't have to do that for bilayer, but for single layer, you have to do that. And so this shape could change a bit. This shape. The DC can change a bit because of that. So that, I think, introduces the biggest uncertainty. Yeah. Okay, so we do it, I would say, the right way, and we see G stars of about up to 14 or so, something like this. And what I like, so that means the exchange field is like maybe 5 times larger than the external field. But what I like about this, in the end, is that you have an exchange field here. There's an average part and there's a fluctuating part. So the average part generates the spin precession, and there's a peak near the Dirac point. Over here, on the right-hand side, you have the fluctuating part, and that's what generated the dip in the non-Hanle data. In the regular data, you had this dip, and that also has its maximum effect near the Dirac point. So these are 2 really different type of experiments, or different things that you measure, and you're seeing the same type of physical behavior. So this is all really telling me that we're really seeing magnetic moments, and we're also seeing exchange fields associated with those moments inside graphene. So we were very happy for this one that we didn't publish as fast as we could, and we just did as many control measurements until we felt comfortable. And I always feel like I'm never 100% happy. I'm always 2% skeptic, but I feel like this work has set a pretty good standard for the field. Okay, I only have a couple of minutes, and I'm only going to show a few slides about this. There's other 2D materials beyond graphene. One is monolayer MOS2, which is direct gap semiconductor, large spin orbit coupling, giant spin splittings. We're working on this. And a lot of people are making this material.
You grow that?
We have collaborators that grow it. Yeah, but it's grown, and we also exfoliate it. You can buy it. There's this material that we've been playing with since the summer. It's called germanane, and I want to spend more time on this. So this is like graphene, except you replace the carbon with germanium, and you tack on hydrogen. So it's more like graphene. So this is germanane. It's a direct gap semiconductor. The band structure is tunable. At least theoretically, it's tunable by changing the hydrogen to other functional groups. And because germanium is heavier than carbon, you should expect to see spin orbit effects, like quantum spin Hall effect. And because it's direct gap with spin orbit, you can study spin dynamics. And we're trying to do it also with alloys with silicon and tin, so you could change the amount of spin orbit coupling coming from the lattice. And the reason why I'm showing it to you is that this last point, we can grow this by MBE. And
On what?
I will show you. I will show you. It's not perfect yet, but on germanium, basically. But I'll show this to you. And so what you do is you start with germanium, and then you grow calcium germanide by molecular beam epitaxy. So you co-deposit calcium and germanium. People had never done that before. They sort of put calcium on and let it diffuse into the germanium. But to try to control it better, we want to do co-deposition. And then the last step is you immerse this into a hydrochloric acid solution. The chlorine is going to pull out the calcium, make calcium chloride, and the hydrogen is going to make the hydrogen terminations. And you get germanane layers. And one of my collaborators at Ohio State had done this for bulk crystals, and he told me, hey, can you do this by MBE? And I wasn't sure, but I thought, yeah, I'll try it, because it would be great if it can work. So a good undergrad did this. So here's the electron diffraction and read patterns. That looks very nice. And when you do co-deposition under the right conditions, you actually get these kind of diffraction patterns. And you can't tell much about it other than it's flat surface and it's ordered. So I say, yes, the MBE is successful, right? Because if it looks spotty or shady, and that's not good. But this looks as good as the substrate, so it's very nice. But it's different. And then, to convince ourselves, we had to grow a very thick film and do X-ray diffraction. So this is just the substrate. That's the substrate peak. If you look at this 150 nanometer film, we see only one additional peak. And that's exactly where you expect to see the germanane, the GEH. Right, so this additional peak corresponds to the germanane. So we're very happy. We take this sample after it's been dunked in hydrochloric acid and put it back into the MBE chamber, do the electron diffraction, and we actually see a 2D-like pattern. I won't explain what that means, but it's a 2D-like pattern, so it's still really flat after all that chemistry, chemical processing. And then we did a Raman spectroscopy, which we didn't think is possible at first, because if you look at the germanium reference, the substrate is a really large peak, and the orange is the one with the film. And so we see an extra peak, and the shape is changed. So if you do a Lorentzian peak fitting on this, and you even let the peak positions move, you see one peak here, another peak there, another peak there. So basically the largest peak is the substrate, and then these three peaks are what you see when you do Raman on bulk crystals of this material. So now we see the same peaks in a thin film. Actually a pretty thick film, but it's a film. So these additional peaks correspond to germanane. So after we did the Raman and we did the X-ray, we were convinced we had the right stuff. So that was really cool. And then
this is a multi-layer. So.
It's a multi-layer. It's a multi-layer. So we want to get it really thin, and so the experiments are happening now. I'll tell you later what we're trying to do. Because we're trying to go on something that's not germanium. And I will know hopefully in a week if it'll work or not. Okay, but we looked at also with atomic force microscopy, because once you see the nice read patterns, you want to do the AFMs. So we look at the substrate, and the substrate is never perfectly flat. So there's a half-degree miscut. On this one, it turns out this terrace, the terrace widths correspond to 0.2 degrees of a miscut off of 111. And then you do the MBE growth. What happens actually is the terraces are getting bigger, so this material wants to make it flatter, right? So this is the calcium germanide. And then you dunk it in HCl, and then, yeah, it looks really nice. I mean, there's still, it's only a few microns, okay? And this is multi-layer. This is 5 nanometers thick. Still multi-layer. We're trying to get it down to single layer. That's our goal. Or even, I don't even know if single layer is critical, because I bet these layers are relatively decoupled. So I don't know if it will prohibit the 2D physics from showing up. It's a question mark. So like in graphene, they're really close. They interact a lot. But this is a little bit further away, so it might not be catastrophic to have multi-layers in terms of the 2D physics. And then we looked at the roughness, we narrowed down to patches to not include the terrace steps. And actually, they're on the order of a few angstroms in RMS roughness within the terrace. So within the terrace, the germanane is roughly atomically flat. We could even see atomic steps inside some of these terraces. So that's pretty good. So one thing is we want a better substrate to just try to make this thing flatter and bigger.
Okay. Why do you have such an angle?
Because when you buy it, they only give you a certain tolerance. So if I want something flatter, I'll have to buy it in a special order and just wait.
Or do it yourself or something.
Or do it yourself. Yeah, I don't have the tools to do that. Like you need a goniometer on an X-ray Lowy, and then you somehow line that up really well, and then you move it onto the polishing stage, which also I don't have, and then.
Sounds simple.
It sounds simple. Exactly. I could draw a PowerPoint of it and get it's done, right? Okay. So anyway, so I'm going to summarize. There's 3 main points. One is that, graphene is a really excellent material for room temperature spin transport. Okay. There's a lot of games that can be played with doping. I think there's a lot of games you can play with doping graphene and other 2D materials with add atoms. So the best result we've had so far is this work with hydrogen with magnetic moments and exchange fields, but we've done a few other works on it. And finally, I'm super excited about this new 2D material that we're able to make by MBE. Hopefully there'll be some good physics, but no guarantees yet. Okay, and anyway, that's all. Thanks. So if there are any questions, I'll take them now. Or, yeah.
Germanane is it's 1-for-1 germanium hydrogen.
That's 1-for-1 germanium hydrogen, yes.
Perfect that way, or so we suppose.
Perfect. In a PowerPoint, it is perfect.
Yeah. In your pictures.
Yeah. It's like that. And my collaborator has been able to put methyl groups like CH3, and it actually changes things like the photoluminescence efficiency like skyrockets when he does that. So it's actually a really great system because the sp3 bonding is the thermodynamically preferred state for germanium and silicon, and but not for carbon. Actually, carbon wants to be more like graphite.
But you
Yeah,
can do carbon,
I mean, so like.
if you put enough hydrogen on that you've got a monolayer,
Yeah, so people have this all started by doing all this type of work with hydrogen on graphene, but the changes that you get are really drastic. It's like from conducting to insulating. It's very drastic changes. You could see how it changed the conductivity, resistivity by a lot, and also that system is not thermodynamically stable. You heat it to room temperature and then the stuff shoots back off. So this, in principle, is a much, much better system to be trying to play these games.
Stronger with the germanium.
Yeah. So even trying to get pure germanine without the hydrogen, that's not flat. I mean, it'll want to buckle. Even theoretically, it'll want to buckle. Right? So for these systems to try to do covalent functionalization, this is really a beautiful system. I mean, the only reason people haven't done it is because there has not been the material, but we're sort of getting there. So I think it's pretty exciting. Yeah.
With this new material,
Yeah.
do you expect an opening of a gap because of spin-off decoupling? Is it good option?
Yes. So if we got the version that didn't have hydrogen or was only slightly buckled, that's a Dirac material, and the gap is predicted to be about I think it's 50 MeV, which is a good size gap for quantum spin Hall effect and things like that. I mean, the most exciting prediction of this class of materials is the one with tin. So Xiaocheng Zhang has a preprint up, and you're able to get a spin orbit gap of about 300 MeVs, and a regular gap of about 300 MeVs also. And by changing the functionalization, what terminal groups you put on there, you can convert it from a regular insulator into a topological insulator. So it's like controlled by the chemical bond. So that is like super exciting.
That would be exciting.
Yeah. So anyways, yeah. We're going to try that. Anyways, yeah.
So can you replace hydrogen by some magnetic impurities with Biggers, with moment?
Okay. Yes. So there was a big thing. So we spent over a year putting cobalt on it. Everyone said cobalt was the thing you wanted. It interacts very strongly, and some people, there was rumors that people saw Kondo effect with cobalt on graphene in STM studies, but that never came out. So maybe it wasn't right. And so we tried, and we gave up, and then moved to hydrogen to try to do something completely unrelated to magnetism. Okay, and so that was very odd. And so Jaroslav Fabian had this idea, coming back to this resonance business. So when you put carbon on cobalt on graphene, it doesn't change the resistance in the same way. It doesn't like skyrocket that resistance like hydrogen does. So hydrogen creates some resonance scattering site, right? But the cobalt doesn't. And so the thought is, because you have some kind of resonance scattering or some localization, maybe that's really enhancing the exchange coupling. And that's why you see it with hydrogen, but you don't see it so easily. Well, we haven't seen it. You don't see it with cobalt. So we're going to try to do an experiment where we put cobalt and we try to make a resonance scattering site with vacancy or something and see if we could see the exchange coupling from the cobalt.
But so experimentally, so when you try to put cobalt, you don't see much change in the resistance. We see similar things to if you put like magnesium or some other. It's charged impurity, so it's long range. So the direct point's going to move, and the slopes of the curve are going to go down. So there's mobility reduction, but the conductance minimum changes a little bit, but it's not like collapsing. So that's what it behaves like. I can't tell the difference between that gold and magnesium. They all do the similar effect. Yeah. But hydrogen is totally different. Yeah.
That other material, MOS2.
Yes.
It has a big gap.
Yes.
Are you studying transport on this material?
Oh yes. Yes. And we're trying some optics too. But, yeah. So the transport is tricky because it's a semiconductor and it's very thin, so the resistance is very high. And when we put down contacts to it, there's Schottky barriers. So our first sort of completed work in MOS2 was to study Schottky barrier formation. And it's really confusing because normally you think about a Schottky barrier, you put things down and they form a Schottky barrier into the material. But in this case, into the material is 1 or 3 atomic layers. It's like very thin. So the thought is that the Schottky barrier happens, but it's going laterally, maybe. And the fact that you have this kind of depletion, for one thing, it's possibly problematic for spin injection or spin Hall effects, which we're trying to do in here. And the other thing is, if you're trying to do 4-probe contacts, you just can't place them on top like you can do sometimes in graphene. You gotta, we haven't done this yet, but we realized that if we want to do 4-point probe measurements, we have to etch it down and have the contacts far, far out of the channel. Otherwise, they'll just remove the carriers and make 4-point probe make no sense, right? So I think that the transport measurements is very tricky, and getting ohmic contacts and so forth is also very tricky, and we're working on that aspect right now. The most work in the material is optics, like circularly resolved PL, also studying excitons. There's very strong exciton binding energies and so forth. Yeah. Is
it possible to dope it with a gate into
yes.
a valence band, or is it too big a gate?
We have done it. We had to apply over 100 volts. And people have done it. Like people have made transistors where you go far into the p-type. You put on hafnium oxide thin and a top gate, and with just like negative 10 volts or something, it's p-type. So that can be done. Yeah, the p-type is the interesting side, right? The p-type has all the spin splittings and the different valleys, polarization, and the spin polarization. That all happens in the valence band side. So that's what we'd love to have.
This is rather unusual spin-orbit splitting.
Very unusual.
This looks like just xenon splitting.
Yes. It's xenon splitting, but it has opposite sign for the different valleys. Yeah. And so, so there's theoretically, the fact that you have some huge internal field, that's going to suppress lots of spin relaxation processes, like the Diakonov-Perel type of, it's like this internal field is so huge that it's like those are all wiped out. And then things like spin, even if you dope it exactly Fermi level up here, then you're going to inhibit spin flip scattering because it can't flip into there, and it has to actually it has to cross the Brown zone to get a spin flip. So there's only certain types, like atomic magnetic scatterers can cause that, but a lot of spin flip scatterers won't satisfy those conditions. So at least theoretically, it's like, yeah, this should be longer spin lifetimes. But anyways, so there's a lot of interesting stuff that goes on in the valence band of this class of materials, and we're trying. It's very hard. We haven't had success yet. So in either of these two materials, we haven't had success with spin or valley yet. There's been some success with valleys here, and I think a little bit with spins, but they're all optical. right? So I think, yeah, I think that this is super new directions, but in PowerPoint still, not in experiment. Yeah. Yeah. All right. Thank you.
I'll be in my office. I have to leave at 6. I think yeah, so I said yesterday because I was busy all day long, and I said I would be available after